Okay, so the next part that we are supposed to learn is electrical conduction. Okay, before we learn about electric current, okay, we are going to learn a little bit about potential difference first. Now, electric potential for the first thing. Okay, electric potential means that how, let's see, okay, I'm gonna take things to chonting right now. Okay, so when we talk about electric potential, we previously learned about electric field strength. Okay, so I'm gonna show a little bit over here right now. Okay, let's talk about water stream. All right, let's talk about water stream first. So water stream is moving from, normally when it rains down from the clouds from the sky, it normally there's a high mountain, so the water will actually reach at the mountain area, and then the water will flow from the mountain area downwards to the stream, to the waterfalls, and then passing through the river, and then finally it will join back down to the sea. Okay, so this is the river, and then this is where the sea is located. Now, why does the water flow downwards actually? Anyone knows? Why does the water flow down?
It's moving from area of higher gravitational potential
It's,
energy.
it's moving from a higher potential energy, gravitational potential energy area. So here, right, when we are from the surface of Earth up until a certain height, okay, it will have a gravitational potential energy. And then towards the sea, the gravitational potential energy is lower. Okay, so it's gravity that allows the water to flow from the mountaintop or from the hilltop down towards the river and then towards the sea. So, in a way to say, the water, all right, water current to be more exact, the water current will flow from a high gravitational potential energy to a low gravitational potential energy region. So the high gravitational potential energy is the mountaintop. Okay. The low gravitational potential energy is the sea. Okay. So water current will flow from a high gravitational potential energy towards a low potential energy. So what does this have to do with electric current that we are learning right now? Okay. So when we have a normal circuit like this, a normal power supply connected to a light bulb, for example. Okay, let me show you my simulation better. Okay, I have a battery showing you the values. Then I'm gonna connect it with circuit, the switch over there. Bring it downward. I'm gonna put a light bulb. Okay, assuming ideal cases. Ideal cases means that um the wire has no resistance and then the battery has no resistance in it. Okay, this is ideal case because in real life situation, the wire has resistance, the battery also has resistance. So over here right now, this circuit is an open circuit. Open circuit, why? Because the switch is not the switch is open. All right, the switch is off. So when the switch is off, the value of potential difference coming out, sorry, the in your terms is known as voltage that you learned previously. All right, but in physics we call it potential difference. All right, I'm going to use voltage for the moment because I haven't introduced the word potential difference yet. So the voltage of the battery is 9 volts, but because the circuit is still off, all right, it's an open circuit, the switch is still off, all right, the electron charges cannot move around. There, the light bulb cannot lights up. So I'm just going to very quickly put a ammeter over here to show the value of the current flowing. Okay, there's no current flowing, so that's 0.000 ampere. Okay, so over here, all right, the longer line is positive normally. Remember, the longer line is positive, the smaller line is negative. So what you learned previously is current flow from which terminal to which terminal. All right, answer back in the chat box again as usual. Current will flow from which terminal to which terminal? MIA already so fast. Current flows from negative to positive? Current you all learn negative to positive, negative to positive. Yes, current will flow from positive to negative. All right, current will comes out from positive, flowing through the circuit, passing through the light bulb, causing the light bulb to light up, and then back to the negative terminal. Okay, so this is the direction of current flowing. Now, recall just now, water current flow is because it is moving from a high gravitational potential energy to a low gravitational potential energy. There's a reason why I use this analogy, because electric current, all right, electric current, also the same situation. It flows from a higher potential energy region, okay, a high potential energy region to a low potential energy region. But in this case, it's not gravitational potential energy, obviously, it's electric potential energy. So if current flows from high potential energy to low electric potential energy, and current, from what you learn, flows from positive to negative, this means that the positive is a high electric potential, okay, and negative is low potential energy, electric potential energy. So in this case, if let's just say for example, I have the battery is 4.5 volts, okay, connected to a light bulb. So which means the majority of the 4.5 volts belong to the positive terminal. The negative one belongs to 0 volts, because high potential energy to low potential energy, current will flow from positive to negative. And like water current, electric current flows from high potential energy to low potential energy. Okay, that is one concept you learned previously in Form 3, if I'm not wrong. That current flows from positive to negative. Okay, so right now, if it flows from high potential energy to low potential energy, then which means there is a potential difference. Okay, so here the word potential difference, based on your textbooks also, a potential difference means from a higher potential to a lower potential, you see, P is connected to positive, Q is connected to the negative part. So when the battery is connected to a bulb in a circuit, it creates an electric field along the wires. So when the battery is connected to a bulb, positive, the electric field will be coming out, negative, the electric field lines will be entering. Okay, so the positive terminal at P has a higher potential and negative terminal at Q has a lower potential. So I think you might need to screenshot this slide if I'm not wrong. Okay, so the potential difference between the two terminal will cause the charge to flow from the across the bulb in the circuit to light up the bulb. Okay, this sentence in a short while I will mention to you. Okay, work is done when the electrical energy carried by the charges is dissipated as heat and light energy after crossing the bulb. So I'm sure you're a little bit wondering what this sentence means. So we'll use the textbook definition. Okay, so textbook definition of potential difference, okay, is this one. Work done, alright, potential difference is the work done, W, in moving one column of charge from one point to another point. So, which means that if I were to have, okay, a column of charge, so I'm going to draw one column, okay, this is my column of charge. I take the column of charge moving from, because in circuit, what charges that move? Positive or negative or neutral? What charges move in the circuit, in the electric circuit? Good. All right, thank you, Hans. Negative charge will move in the electric circuit. So when I take one column of electric charge, all right, of negative charge, moving from point Q to point P, okay, moving from Q to point P, I'm going against the electric field, all right, which means that if in this situation, if I have a boat, all right, assuming that's a boat, okay, if I have a boat and I'm moving this boat upstream from low gravitational potential energy going upstream, we will definitely have to do work, isn't it? Because we are going against the water current. We are going against the water, the direction of the water flowing. Okay, so when you have to do work, that is what we considered at electric potential difference. We need to take one column of charge, all right, to move from point Q, which has lower potential, going against the electric field, okay, to reach point P. The amount of work done, all right, to bring one column of charge from point Q to point P or from one point to another point, that is known as potential difference. Okay, so this is what it meant here. The work done when one column of charge move between 2 points in an electric field. Okay, so from the definition, potential difference, V, is the work done, W, over the charge, because one column of charge. So work done can be interchanged with energy. Okay, you can either use W or you can use E depending on you. All right, depending on the question also. So always remember, W and E can always interchange. Work done and energy can always interchange. So here, the SI unit for potential difference V is joule per column, or normally we use the SI unit as volts. So the potential difference of 1 volt, if the work done to move one column of charge from one point to another point is 1 joule. That means in order to bring one column of charge from Q to P, it needs to use an energy of 1 joule. All right, so that is the meaning of potential difference. So for here, are you all okay? Was it too fast, too slow, confusing? Okay, all right. So that is potential difference. Now, why did I show you potential difference first? Because you see over here, all right, here is the positive part. How do I know it's the positive part? Because in the battery, the part that comes out, that is the positive terminal of the battery. All right, the flat surface, that is the negative terminal of the battery. So, which means the yellow or orange color one, okay, that is the positive terminal. The black color direct side is the negative terminal. Okay, so the yellow color side, the positive terminal, has higher potential difference, which is 9 volts. And then over at the black color, it's low potential energy, which is 0 volts. So you see one thing right now. How does electric current move? Last time you only learned that electric current move from positive to negative. Now, electric current happens in the sense that if, let's just say, okay, I close the circuit. All right. This is a complete circuit right now. Complete circuit. Why? Because everything is joined up together. But do you notice one thing? The light bulb is not on the ammeter. The ammeter has no reading as well. All right. You would probably know why there's no reading. Do you notice why there's no reading for the ammeter over here? And the current is not light up. Anyone knows why? All right, 0 volts. There is no value of potential in the circuit. The whole entire circuit is 0 volts right now. So what do? I need to increase the volts. All right, I need to increase the value of the potential difference. You see, the minute I increase it, the minute I increase, the current will flow from positive terminal of the battery, passing through the ammeter showing the current of 0.3 ampere. The light bulb is on, and then it goes back to negative terminal. But then one thing, how did this current happen? All right, so I'm gonna show you another method. This is the electrons moving. All right, electrons is mainly at the negative terminal of the battery. So electrons will move from the negative terminal of the battery, passing through the rest of the circuit, going through the light bulb, passing through the ammeter, and going back to the positive terminal. When the current passes through the light bulb in a complete circuit, all right, when the electron move from the negative terminal to the positive terminal through the circuit, then only there will be current flowing. Okay, so wait, let's see. I want to bring something out. Okay, so this is 3 volts. Look at the current. The current is actually 0.3 ampere. So please take note as sketch at the side there, because I'm going to increase the potential difference right now in the battery. All right, the power supply supplied by the battery. So I'm going up to 11 volts. So when it's 11 volts, what happened to the flow of the electrons? Can someone tell me what happened to the flow of electrons comparing to 3 volts just now? So this is 11 volts. I'm going down to 3 volts. Look at the flow of the electrons. Good. All right. Comparing to 2 volts or 3 volts, and then I go to 11 or 14 volts, the electron flow faster. When the electron flow faster, the current is also higher. So remember, I always said that in physics, we need to know what is the cause and what is the effect. Okay, so over here, you need to identify the cause and the effect also. So I'm just going to bring this up. Okay, so when we increase the potential difference, okay, increase the power supply. All right, when we increase the power supply by the battery, what happens is the potential difference will increase in the circuit. When the potential difference increase, the electrons or the negative charges in the circuit will move faster. Okay, so when the electrons and the negative charges in the circuit move faster, this actually allow higher current to flow, and hence the light bulb shines brighter. All right, so this is the flow of the cause and the effect. It all started from the battery. If the battery has no charges flowing, there's no electric potential in the battery. All right, if there's no electric potential in the battery, there will be no potential difference in the circuit. Okay, so when this happens, if there's no electric potential in the circuit, the current cannot flow. All right, let's go back to this simulation again. Okay, if again I put 0, all right, there's no value of electric potential at the battery, the current is not moving. Why the current isn't moving? Because there's no potential difference in the circuit. So in order, when there's no potential difference in the circuit, the current doesn't flow. The electron doesn't flow. There's no value of current, and then the light bulb will not be on. But as I increase the value of the electric potential in the battery, more electrons is moving and it's moving faster. When it's moving faster, there's current flowing, and then the light bulb is brighter. You can see it brighter because the yellow color lines get longer. Okay? So electric current's actual definition. I hope that you understand this whole flow of things. Electric current's definition, okay, according to our textbook, is the rate of flow of charge in a conductor. Okay, so the rate of flow of charge in the conductor means how fast this electron is moving. All right, how fast this electron is moving past the light bulb. All right, the faster the electrons is moving in the light bulb, the stronger the amount of current. The value of the current is 2.9 ampere. Okay, and it will cause the light bulb to be even brighter. So please take note of this situation. The brightness of the light bulb depends on the current flow. If the current flow is stronger, the light bulb will also be brighter. But how do we get the current to become even more? Again, back to the situation that I wrote just now. All right, you want higher current, you need to make sure the electron move faster. How to make the electron move faster? The potential difference in the circuit needs to increase. How to make the potential difference increase? Use a bigger value of battery law. Okay, so definition of electric current from your textbook is the rate of flow of charge Q in the conductor. But then again, you would notice one thing. The definition of electric current is the rate of charge flow. Did they say rate of negative charge or electron? No, isn't it? It did not mention that it has to be electron. It did not mention that it has to be negative charge. It just mentioned that when the when the charge is flowing in a circuit in a conductor, the rate of flow is actually the electric current. So if positive charge, is it possible for positive charge to flow in the circuit? Possible, but very unlikely. All right, it is possible but very unlikely. Means what? It's very difficult, lor. Why is it difficult? Because normally the one that moves around easily is free electrons. All right, you know that electrons at the outermost orbit, the attraction force from the nucleus is very, very weak. A little amount of energy that electron can go away already, easily shared away. So electrons normally flow in the circuit, and that's why we characterize the net charges that flow in the circuit are electrons, negative charges. Okay, so electric current is the amount of charge flowing per time, all right, per second. So electric current will flow from positive to negative terminal, while electron will flow from negative terminal to positive terminal. Remember this, electron move from negative to positive, current move from positive to negative. Okay, so the definition of electric current I is Q over T, because electron is the flow of charge per unit time. Rate of means divide by time. Okay, but normally we don't go and memorize as I equals to Q over T. It's easier for us to memorize it as Q equals to IT, where Q is the total charge. Over here, Q is total charge, because the other symbol of Q happens to be in Form 4 heat chapter. Q represents heat energy. But if you see the current over there, so that Q represents total charge, right? I is current, time is in second. Again, to remind all of you, whenever we deal with a physics formula, it has to be SI unit. So the SI unit for current is ampere, the SI unit for charge is coulomb, the SI unit for time is second. Okay, so remember that whenever we want to play around with this formula, um, it has to be the SI unit. Okay, now a very quick thing that I want to share with you. Okay, can I ask right now? You all have power bank, right? Okay, let me target one power bank from the next table first. When you get a power bank, how do you choose power bank? How do you choose the power bank? Or people buy for you? Biggest capacity, 10,000 mAh, 20,000 mAh, correct? Okay. So let me show you one thing, and the weight also, and the size also, right? 20,000 mAh. Okay. Watch this, What do you think M stands for? Good. Daryl found the answer. M is milli. A stands for ampere per hour, Daryl done. This is all to the power of 1, eh. So milliampere hour. Ampere is the unit for Ampere is the unit for current I. Hour is the unit for time T. I multiply current multiply by time, what do we get? Q. So 20,000 mAh is the amount of charge that is inside that power bank. All right. It's the amount of charge inside that power bank. So meaning means, okay, uh very quickly, okay, this is 20,000 mAh. Let's just say you use normally when you want to charge your power bank, okay? When you want to charge your power bank, your cable and the power charger, I have no idea where's my all my stuff. Suddenly all my stuff is not with me. All right. The power, that socket, okay, the power supply, that particular plug, okay, it writes there 2.1 ampere, which means that you are using 2.1 ampere to charge your power bank. How long does it need to take for you to charge your power bank if your power bank is a 20,000 mAh? Okay, so I'm going to erase this off. So for those of you who have 20,000 mAh power bank, how long do you take to charge your power bank? You don't even have the answer. A day maybe. Okay. Now watch this, Okay, I use a 2.1 ampere current to charge my power bank, okay, which is 20,000 mAh. So I want to know how long does it take. So again, when I mention this, okay, whenever we deal with this a physical physics formula, we need to make sure that it's in the SI unit, whereby the milli is not in SI. All right, the SI unit for current is ampere. Okay, so I need to convert this Q, which is 20,000 mAh, 20,000 milliampere hour. I need to convert it to ampere first. Okay, so my Q is 20,000 milliampere hour. Milli, when you press your calculator, those of you who's having FX570MS, milli is 10 to the power of negative 3 ampere hour. So negative 3 means to cancel off 30 lor. So 20 ampere hour. Alright, that's the amount of charge. So I want to know how long does it take to charge the power bank. So using the formula Q equals to IT, T time is the charge divided by the current. I'm using a 2 ampere current. So here charge is 20 ampere hour. The current that I'm using is 2.1. So 20 divided by 2.1. In order to charge the power bank 20,000 mAh using a 2.1 ampere current, it takes you 9.5 hours to charge it. That's why sometimes you say it takes you a day, Lester. So if let's just say even worse, you go and use a 1.0 ampere punya cable and charger, then it will take even longer. Lor. Same thing goes to your handphone. Your handphone will be roughly around 4,500 mAh only. So how did the manufacturer and the supplier allow you to charge your phone faster? You would notice that a normal charger, all right, a normal charger supplies 2.1 ampere. Not step up transformer, but they give you a 3 ampere. My Huawei charger is actually a 3 ampere charger. And nowadays, when you look at the handphone, the latest handphone nowadays the current supply is 5 ampere one. That's how they supercharge it. Because if it's using 5 ampere, then it will cut short from 4.5 hours to charging up to 4 hours only. So that is how they manipulate the time for you to charge your handphone or to charge your power bank. Okay? All right. So, but then one thing, if you use a higher current input, your handphone and your battery, you find that it heats up faster because the charge is moving in too fast, too many frictions going on inside. So it might heat up, and that's why sometimes when you charge using a higher value, yes, Conway, the answer is correct. Boom. Long term wise, it will definitely cause it to explode in a way lah. Okay. Now, so that is a little quick out of the topic lah. Okay. So another formula that I want you guys to write down is this formula. Again, it's in the standard curriculum, but they didn't put it inside the textbook. Electric charge. Electric charge is donated by the symbol Q. Okay. So the unit for electric charge is in column. I'm not sure if you learned this in Form 3. Okay. Q formula is equals to Ne, whereby N represents the number of electron, E represents the charge of electron, which is 1.6 times 10 to the power of negative 19 column. So let's just say one thing according in your textbook. Write down already or you screenshot already? Okay, 5, 4, 3, 2, 1. Now, in the textbook, you will see at a corner, I've forgotten which page, exactly this page, at page 99. At page 99, you will see this bright info. Charge of an electron is 1.6 times 10 to the power of negative 19 column. Then they said 1C equals to 1 over 1.6 times 10 to the power of negative 19. If you were me lah, you would question mark apa ini. Okay? Because I'm sure they didn't show the symbol, the formula on how they got this thing at that side. So the formula comes from Q equals to NE. All right. They want to know how many in one column of charge, all right, or in one column of negative charge. Okay. How many electrons is present? All right. In one column of electric charge, how many electrons is present? So in order to get that formula, you need to use this. Please do take note. This particular formula is inside the syllabus, but it's not in the textbook. That's why I'm teaching you this. So Q is one column. We want to find the number of charge. Electron here, the charge of electron is 1.6 times 10 to the power of negative 19 column. So N equals to Q over E, and Q is one column. Electron charge is 1.6 times 10 to the power of negative 19 column. Cancels off the C. This is what you get that they write over here. So press this into the calculator, you get 6.25 times 10 to the power of 18 number of electrons. So this is what this bright info showing. Okay? So up to here, are you alright? Okay, let's see. Okay, so up to here, we are done with subtopic 3.1. We will go to subtopic 3.2. All right, subtopic 3.2 is at your page 100. Okay, now page 100, let's talk about Ohm's law. Okay, let me close this first. Don't save. Okay, I want to talk about Ohm's law. Where's my Ohm's law? Textbook didn't really mention about Ohm's law, but I'm still going to teach you to recap what is Ohm's law. Okay, so for those of you who, if you want this, do you want this slide or you want to screenshot the thing? Later, ask me for it. Okay, Ohm's law, it was from last time that you learned in Form 3, but again, I'm going to mention it over here because the first part of the subtopic 3.2 tells you about ohmic conductor and non-ohmic conductor. So, first thing first, let's know about the relationship between current and potential difference. So, here, the potential difference is 2.29 volts, the current is 2.90 ampere. Now look at the relationship. Okay, I want to see the relationship. I'm going to put a current over there for you to see side by side, top and bottom view. Now, if I were to increase my potential difference, what happened to my current? If I increase my potential difference, my current will increase. When I decrease my potential difference, my current also decreases. Okay, so here the relationship between current and potential difference is the greater the potential difference or voltage, the greater the current flow. Now try to avoid using the word voltage in this chapter already onwards, because starting from now you should learn how to use the word as potential difference, even though it's the same thing but different places, different situation. Because technician, all right, technician are people who deals with electricity. They 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 don't call it potential difference, they call it voltage. In physics, we call it as a potential difference. So, will you get penalized if you use voltage in SPM? No, you won't get penalized. But we try to encourage students to use the word potential difference. It's the actual meaning, and we're learning physics. You're not learning to be a technician. Okay? So, when the potential difference between 2 points in a circuit increases, the current flowing through the circuit will increase as well. So when the potential difference between the points decreases, the current decreases. So in a way to say, the conclusion of the relationship between potential difference and current is that they are directly proportionate. All right. When it is directly proportionate, this is the actual Ohm's law definition. Okay, because I know whenever we talk about Ohm's law, student always say, what is Ohm law? Student will say V equals to IR. So unfortunately to tell you, V equals to IR is not the definition for Ohm's law. It's not even the formula for Ohm's law. Okay, but in order to simplify lower form, they tell you it's Ohm's law. I'm telling you right now, the actual definition of Ohm's law is the electric current flowing through a conductor is directly proportionate to the potential difference across it. Okay? With the condition, this condition must be mentioned if they ask you what is Ohm law. With the condition that the temperature and the other physical condition must be constant. Meaning means that whenever you connect the power supply through a conductor, let's just say, like, for example, this light bulb. All right, obviously this light bulb I can consider it as a ohmic conductor. Why? The current doesn't change. It's a simulation. Okay, but in real life situation, all right, real life situation, let me switch a real bulb here. A real bulb in life. Okay. All right. A real light bulb in real life, when you let electricity pass through the real life light bulb, it will heat up. So when it heats up, it no longer obeys Ohm's law, because when it heats up, the temperature change. Okay, so for Ohm's law, all right, for conductors that obeys Ohm's law, the electric current must be directly proportionate to the potential difference, with the condition that the temperature and other physical condition meaning means the cross-sectional area of the wire, the type of wire used, it's all constant. You're using the same wire. But the most important part is the temperature must be constant. All right. So if the temperature is constant, the electric current and the potential difference is directly proportionate. When it's directly proportionate, the graph, all right, the graph of potential difference against the current, it's a directly proportionate starting from the origin. Okay. When it starts from the origin straight line graph, this is a Ohm's law graph. Okay, so Ohm's law, the gradient, we know gradient, we take y-axis y2 minus x1 divided by x2 minus x1, meaning means y-axis divided by x-axis. So in this graph, y-axis is the potential difference, x-axis is the current. So the value of the gradient of potential difference divided by current is a constant value. Having that is a constant value, which means that it is resistance. That gradient of potential difference against current is the resistance. So resistance definition is the ratio of potential difference across the conductor, sorry, the ratio of potential difference to the current flowing through it. So resistance R is the ratio of potential difference to the current flowing through the conductor. So that's how we rearrange this formula and we get V equals to IR. Okay? Ohm's law is potential difference directly proportionate to the electric current with the condition that the temperature is constant. Resistance is the ratio of potential difference across the current. Rearranging it, you get V equals to IR. Okay, so now I'm clarifying what you previously learned, that Ohm's law formula is V equals to IR. All right, Ohm's law is potential difference directly proportionate to the current flow. Okay, resistance is the ratio of potential difference across the current. Okay, so I hope I clarify this for you guys. Now, ohmic conductor. Ohmic conductor obeys Ohm's law. Why does it obey? Because the temperature and other physical conditions are constant, the potential difference is directly proportionate to the current. Non-ohmic conductor does not obey Ohm's law. Why does it not obey Ohm's law? Because the temperature changes. When the temperature increases, all right, for non-ohmic conductor, when temperature increases, the resistance in the circuit could drop, could increase, causing the current I to drop or increase. So it will not be directly proportionate to the potential difference for non-ohmic conductor. Okay, so if you look into your textbook, for ohmic and non-ohmic at page 102. Alright, ohmic and non-ohmic conductor. Ohmic conductor, our graph of potential difference against current, it's a straight line graph passing through the origin. Alright, we call the relationship to be potential difference directly proportionate to current. The rate of increase of the voltage increase constantly. And all right, the resistance, which is the gradient, is a constant value. This is for ohmic conductor. Non-ohmic conductor, we would see a curve positive graph. A curve positive graph whereby the relationship here is increases with I. Potential difference increases with I. Why? Because the resistance increases. Okay, the rate of the increase of voltage increases, but not constantly. So what actually happened? That's what we have in the info gallery underneath that. Okay, the graph on the right shows the relationship between the potential difference V and the current in a tungsten filament bulb. Now, most of the metal, the conductors, they are actually ohmic conductor. All right, so tungsten wire is an ohmic conductor, but as the current flow through the coil increases, the temperature of the coil increase. Then only it causes the bulb to light up. Over here, when the charges flow through the circuit, the current pass through the light bulb. It's a filament, actually. If you look into the simulation here, let me close this, close the value. If you look into the light bulb, all right, our actual light bulb, inside here, this is a wire, an exposed wire. So when charges pass through this wire, it will heat up, and when it heats up, it creates light energy. Okay, it will actually shine. So in this case, this is what it meant. When current flow through the coil increases, the temperature of the coil increases and causing the bulb to light up. So at the same time, this is the key condition. At the same time, when it lights up, the resistance of the coil will increase with temperature. The higher the temperature of the bulb, the higher the resistance. When the resistance increase, the current value slowly drops. So under this condition, when the temperature cannot be kept constant, the tungsten coil in the bulb exhibits a non-ohmic characteristic. Okay, which means this value, all right, when it's coiled up, it will cause the light bulb to be considered as non-ohmic condition. Okay, so that is for ohmic and non-ohmic. Ohmic conductor means it obeys Ohm's law. The potential difference is directly proportionate to the current. Resistance is constant with the condition temperature is constant together with the other physical quantity. Non-ohmic conductor, the potential difference increases with the current. Why? Because when the current flows through it, the temperature increases, the light bulb lights up, but the resistance increases as well. All right. So when the resistance increases with the temperature, it is already considered as non-ohmic characteristic. Okay. So that is ohmic conductor and non-ohmic conductor. So up to here, are you guys okay? Okay, all right. So if you guys are okay, I'm gonna give you guys around 3 to 5 minutes break first. Break for me lah. I've been talking non-stop, right? So after that, we'll come back and we will do series and parallel circuit. The front part, not much of exercises. Series and parallel circuit more. As I said, I want to cover electromotive force. Okay, so let's take a quick break lah, huh? your Beijing one so far work meh?
Apparently all spot on though.
Serious.
Yeah.
So far I know physics tak ada lah. Cannot talk so much. Recording. So can we continue? Shall we continue? Um, After we talk about electric series and parallel, okay, according to your textbook, where is it? Okay, after series and parallel circuit, according to your textbook, is supposed to be factors that affect the resistance of the wire. I'm gonna kind of skip this a little bit. Okay, we will try to skip it a bit lah. Okay, so let's now go through series circuit and parallel circuit. Now, I'm gonna use the simulation to show you guys how does a series circuit and the parallel circuit. Have you all learned series and parallel circuit in either RBT or science last time? Ada RBT but in BM. Okay, now I'm gonna show you guys. I have a battery here, so I'm gonna set this up again. If you want to play around with this simulation later, ask from me. I'm not gonna send it to you now. Even if you copy yourself, go ahead and copy lah. Okay, now series circuit is I am taking this out. I'm gonna put a current ammeter here. Alright. That's an ammeter connected to a wire. So again another ammeter to pass through this resistor. Okay, either a resistor or a light bulb. In a short while, I'll explain to you. Okay, even though it's written resistor, but I put a light bulb over there instead. Okay, we don't need to see. One conclusion from the first lesson, the first part of the lesson that we had just now is in order for current to flow, you need the electric charge to flow. And this electric charge that we are talking about is electrons or negative charges. So if there is no charge flowing, no electrons moving in a circuit, there will be no electron flow. All right, so you would understand right now in quantum physics, whereby the electrons is moving, released from the cathode going towards the anode, then only the current actually has value. All right, the ammeter will has value because there is electron flowing in the circuit. When there's electron flowing, the more electrons flowing, the more the electric current. All right, the reading of the ammeter will increase. Now, so what I have over here is I don't want that slide. I want this empty slide. Close this. Okay, so what I have over here is to connect a circuit like this. Okay, I have the power supply connected to a switch. Okay, and then I connect it to a light bulb and another light bulb. Now, because over here, if the current is allowed to flow, I close the circuit, you notice that the current is coming up from the negative terminal of the battery, flowing past through the light bulb and the ammeters, and then getting back to the positive terminal. So the electrons only have one path to flow in order to get back to the positive terminal. This connection is known as a series circuit. If the charges or the current only have one path to flow to get from electrons, if it's electrons from negative terminal to positive terminal, it only has one path to flow, then it is a series circuit. If the current from positive needs to go to negative, only one path to go, then it is also a series circuit. So my analogy for a series circuit is the battery is our house, the positive is our house, the negative is our workplace or our school. the resistor or the light bulb, right? The resistance or the light bulb is known as a police block. Okay, the wires represents the road. So if coming out of your house in order to get to the school, you have to pass through two roadblocks, no other choice, only one road. That's a series circuit. Okay, but if you have another path, for example, okay, I take this path, I put a light bulb here. If you have another road to move, because the top part there's two roadblocks ma. Remember, I used the light bulb to represent as roadblocks. The top part there's two roadblocks. If there's a path with only one roadblock, some of them will go to the top one, some of them will go to the bottom one. Which means from your house to get to the school, you either go through two roadblock road or you go through one roadblock. So you have two paths to go through. So this connection is known as a parallel circuit. Okay, so when it is above and below, this is a parallel circuit. That's how I remember lah. Okay, so I'm gonna take this out. Delete, delete, out of sight, out of mind. Okay, now this circuit. So what we can see is that when the current is flowing from positive to negative, the current that comes out from this light bulb is 0.5 volts, 0.45 ampere, and then the one that comes out from the second light bulb is also 0.45 ampere. The one that enters the battery back is also 0.45 ampere. Okay, so what conclusion can I have from this? Okay, what conclusion can I have from this? So this is a switch. Okay, the current that comes out, I call it the total current. Okay, and then I label this as my R1, I label this as my R2, and then I perasan satu benda, my current direction sudah terbalik. Why the current direction terbalik? Because if the switch is closed, current move from positive to negative. So my current direction should be this direction towards the screen's left. So here, I total, all right, the total current flowing the circuit. So the current that passed through resistor 1, I label it as I1. The current that passed through resistor 2 is I2. Okay, and from the simulation that we see just now, the terbalik already, so I'm going to switch this around. All right, the current that comes out from the battery, I total is 0.45 ampere. The current that enters resistor 1 is 0.45 ampere also. The current that goes into the resistor 2 also 0.45 ampere. So the conclusion I can have for a series circuit, all right, the series circuit, the total current is equals to the current that passed through first resistor is also the same as the total current that passed through the second resistor. Okay, so that is for current. Let's talk about potential difference. Okay, the power supply, all right, the potential difference across the battery. In order to get potential difference, I'm going to take a voltmeter out. So I put this here and I put this here because the direction red color is going towards the positive. Okay, so the potential difference across the battery is 9 volts. The potential difference across the first light bulb, terbalik because of the battery again, is 4.5 volts. Okay, so I'm going to label that. The potential total from the battery is 9 volts. Across the first resistor, I label that as V1. It is 4.5 volts also. So let me measure the second part. Here and here. Also 4.5. This part, V2, is also 4.5 volts. So what is the relationship of my V total, which is from the battery, with V1 and V2? What is the relation? V1 and V2 and V total, what would that be? 4.5 plus 4.5, we get 9. So the V total in series circuit is V1 plus V2. Okay? Now, for resistance, there's no measurement for resistance because in physics we do not use ohm meter. RBT you use ohm meter, but in physics we don't use ohm meter anymore. Okay? So for the resistance in series, how do I memorize the circuit and the calculation? Is that the series circuit is next to each other. Okay? When a series circuit is next to each other, R total, that means the total resistance in the circuit, is R1 plus R2. Okay, so this is series circuit. So how do I memorize here? Because potential difference and resistor, they are both sum. So how I memorize is looking at the series word. In series, all right, there's a spelling of I here. So I is current. So the current, the total current flowing in the circuit is the same as the current entering the first circuit, the first resistor, and it's the same amount of current that enters through the second resistor. So the current in series circuit is the same. So IT equals to I1 plus I2. That is how I memorize my series circuit. Later on, I'll give you a summary. Okay, I hope this one you guys clear. I'm going to change slide in 5, 4, 3, 2, 1. Okay, now I'm going to connect another circuit right now. This time, power supply connected to a switch. My light bulb now is above and below. Okay, so this is my V total, the current coming out from the power supply. This is my resistor R1, my resistor R2. The current coming out entering resistor 1 is I1. Current entering resistor 2 is I2. The potential difference across resistor 1 is V1. Potential difference across resistor 2 is V2. So I'm going to measure the current and the potential difference. Throw this back in. Throw this back in. Open the switch first. So you see, when the current supposed to come out from the positive terminal, there's a split already. So if you look at the electrons can either go to the top light bulb or it can flow down to the second light bulb. Okay? So this one is a parallel circuit. Okay? So you see the current, the electrons can either pass through the first resistor, the top resistor, or the current can pass through the second resistor to get back to the negative terminal. Negative to positive terminal. So the current also has two paths, either passing through the top light bulb or passing through the second light bulb. Okay, just to clarify one thing, you guys notice that I keep on mentioning one word because in electricity, okay, in electricity, light bulb can be a substitute of a resistor. Okay, in RBT, your resistor looks like this. Okay, this is your resistor in RBT. But in physics, we don't use a resistor already, honestly to say. Okay, we don't use this kind of resistor. We normally use a light bulb or we will use a rheostat. Rheostat is a variable resistor. The value of the resistance can be changed. Okay, that is what we call a rheostat. I'll show it to you when I'm preparing you guys for the ujian amali. Okay, so here, if I were to switch on the power supply, remember what I want to measure. I want to measure the current total. I want to measure the I total, I1 and I2. Okay, so I'm going to let this power on. So my outgoing current from the battery is 1.8 ampere. The one that enters resistor 1 or the first light bulb is 0.9 ampere. The one that enters resistor 2 or the light bulb 2 is 0.9 ampere. So if I were to go back to here, all right, if I were to go back to here, this is 1.8 ampere. I1 is 0.9 ampere. I2 is 0.9 ampere. So in a parallel circuit, the total current flowing in the circuit is I1 plus I2. Notice that 0.9 ampere plus 0.9 ampere. So the total one is 1.8 ampere. Okay, so that is current. Next is the potential difference. So in order to measure the potential difference, as usual, I have to bring this. Okay, I'm going to switch the terminal around. It doesn't really matter for us. Let's not see that. So the potential difference across the battery, 9 volts. Okay, total potential difference from the battery coming out from the battery is 9 volts. Then across the first resistor, across the first light bulb, okay, 9 volts also. Then let's try the second light bulb. Also 9 volts. So which means V total 9 volts with V1 also 9 volts, equivalent also to V2, which is also 9 volts. So for parallel circuit, the potential difference is the same across whatever electrical appliances that is parallel. Okay, so what about the resistance? Now, for your information, I'm using a very simplified way for me to tell you guys the connection between current, potential difference, and resistance, because there is actually a derivation, but that derivation is not part of your syllabus. That's why I did not use the derivation to show you. I used the simulation to show you guys the reading. Okay, so for resistance, all right, the total resistance in the circuit, how I do is that resistor light bulb 1 and light bulb 2, they are above and below each other, isn't it? Above and below each other for me looks like a fraction. So 1 over R total equals to 1 over R1 plus 1 over R2. So this is how we calculate the total resistance for parallel circuit. Okay, so this is parallel and this one is series circuit. So I'm going to show you right now how I memorize this too. Okay, sorry if you can hear my girls crying at the background. Okay, so how do I do this? So I'm going to take a table. Okay. All right. So I'm going to use this table. At this part, I'm just going to let it be blank. Nothing over there. Okay. So, why terlebih satu? Okay. So this is series circuit. This is parallel circuit. Okay. Now, when we deal with series and parallel circuit, we assume ideal case. Ideal cases means it obeys Ohm's law. So Ohm's law, the formula that you guys keep memorizing is V equals to IR. Okay, so this is how I put it. So whenever we look at a series and parallel circuit, always remember you have to use the formula V equals to IR also. So how do I put the values in? Remember what I mentioned just now? In series circuit, there's a symbol I and S, right? So the current in the series circuit, I total equals to I1 equals to I2. Okay? So by any chance, can you hear her screaming at the No, right? My elder can. Okay. My elder one always try to scream out loud. Okay, so in series circuit, the current is the same, so you use that to identify that. Okay, and then what you do, the rest in series circuit is add up, remember? So V total equals to V1 plus V2, add it up. Resistance also add up. R total equals to R1 plus R2. Okay, over there. Then what you do is cross this equal sign, bring it on top. Okay, so when you bring it on top, what will we have? For parallel circuit, the total potential difference is V1 equals to V2. And then the rest will be all add up. So I total equals to I1 plus I2. Resistance in parallel is above and below. Above and below looks like a fraction. So 1 over R total equals to 1 over R1 plus 1 over R2. Right? So this is how I simplify, I put the information into a table. Now, what happens next? Okay, how do I simplify it even further? Okay, because normally physicists, we want to make things even further, simplify even further, right? So in order to simplify things even further, okay, this is what I'm going to do. Okay, so here, series again, and then parallel, and we use the formula of V equals to IR. Okay, so my simplified version is like this. In series circuit, the current is the same. So I same. Alright, when I same, I cross multiply to the potential difference in parallel. V same. Then what do I do next? What I do next is, you still remember what symbol does this represent in maths? What does this symbol represent in mathematics? It's the sum. So for the rest of the boxes, put a sum in there. So in series, potential difference is the sum. Parallel current is the sum. Series means next to each other. So it's a sum of a direct resistance. Parallel is above and below, so fraction 1 over R. So this is how I memorize the series and parallel circuit. Okay? I hope this one you're copying down or your screenshot, but I prefer you copy down. Memang tak sempat for me to masuk EMF. So which means next Wednesday we will masuk EMF. When is our class? Our exam is on the Thursday, right? Okay, so 30th we cover EMF. Are you done with this screen? Okay, so since we are done with series and parallel, I think I will just take one example to do the question. So memang tak sempat for us to masuk EMF. I'll cover EMF next Wednesday. Make sure you masuk. So I'm gonna take an example here. Tak suka this example. Let's see what do we have here. Don't be scared when you see so much of resistance. In actual SPM situation, the resistance, the most that they can give you is around 3 or 4 only. Because calculation questions, a student should be able to finish a 3 marks calculation questions within like 3 to 4 minutes, So they won't really give you such a complicated circuit to calculate. Do take note that. Where is the formative practice? Okay. Formative practice tak boleh guna. I'll just take a example, which I think is quite difficult. Okay, maybe I'll just directly explain example 2 to you guys lah. Okay, now when we have a circuit like this, okay, as I previously mentioned, normally in SPM, they will not give you this is 5 resistor in the circuit, all right? You have R1, R2, R3, R4, R5. Do take note one thing, try to label the resistor, all right? Even if you see a light bulb, label the light bulb as a resistor as well, okay? So over here, sorry. Okay, over here, the first question asks you to calculate the effective resistance. No matter what happened in the question, always calculate the effective resistance first. Okay, so effective, only when you calculate the effective resistance, then you will be able to calculate the current or the potential difference. So here you want to calculate the effective resistance means turning this complicated circuit into a circuit with just a power supply and a single resistor. That's the meaning of calculating effective resistance. To simplify this 5 resistor into one. Okay, so my first method in doing that is to redraw. Okay, whenever I calculate resistance, I will always redraw lah. Okay, and main reason why I redraw is because I don't want to see the potential difference at the ammeter over there. I want to simplify what I see. R1 equals to 4 ohm, R2 equals to 4 ohm, R3 equals to 2 ohm, R4 equals to 2 ohm, R5 equals to 4 ohm. Now, how do I change 5 resistor into 1? Is by simplifying the circuit. So some students have a method to memorize, simplify the one in parallel first. All right. But you cannot do that because if you want to simplify the one in parallel, you have the third and the fourth one parallel to number 5. But when you want to simplify number 3 and number 4 to parallel with the 5, you have to join these two first. Join these two resistor in a from a 2 resistor to 1, then only you can convert to R3 with R5. So my first step, okay, is to join R3 and R4. So very quickly, I put a table here. 3 columns, 4 rows. Series, parallel, V equals to IR. So I is the same, V is the same. And then the rest all summation. Series, direct summation potential difference. Current is summation for parallel. Resistance next to each other, but parallel is a fraction. Okay, so R3 and R4 is series. So series means you directly add both together. So I symbolize R subscript 3, 4 is whereby R3 plus R4 because they are in series. And yes, make sure that you write the formula out. And when you write the formula out, make sure you know which resistor you're using. That's why you see R3, R4, R5, R1, R2 in my working. So R3 is 2 plus 2 equals to 4 ohm. So what I did is I turned this circuit into R1, R2, then it splits. my R3 and R4 now becomes like this, R34. And then at the bottom, I have R5. So my circuit like this right now. Then only I can solve this by parallel. Okay? So I am going to highlight this. Wait. Okay, bring this up. Okay, now simplify that already, ma. So my next part is to simplify R3, 4, and R5. They are above and below each other, which means they are parallel. So 1 over R, up to you lah. You want to use A or B or C because I know what am I doing, so I'm writing R3, 4, 5. Whereby R3, 4, 5 is R 1 over R3, 4 plus 1 over R5. Okay? Everything I write so big, nanti tak ada tempat lagi. One over R345 equals to 1 over R34 plus 1 over R5. R34 is 1 over 4. Alright, the one that you calculated. R5 is also 1 over 4. So which is 2 over 4. This is R34 ma. Therefore, R34 is terbalikkan 4 over 2 equals to 2 ohm. So once I got this, this circuit now becomes R1, R2, and R345. And R345 is 2 ohm now. So finally, R effective. I can write R effective or R total. Why? Because these 3 remaining resistor now is in one straight line, all in a series circuit. So R1 plus R2 plus R combination of 3, 4, and 5. So that would be 4 plus 4 plus 2, 10 ohm. Okay? I hope you guys are okay with that. Are you guys alright? Jangan nanti pandang short sendiri aja kat sini. Hopefully okay ah. No response means consider okay ah. Okay, good. Thank you for the response. Okay, so the next question that the textbook asks us to find is the current flowing through the ammeter. We know from just now our calculation of effective resistance is 10 ohm. Now they want to know the current flowing through the ammeter, and the ammeter is here. Now, how do we know which current are we calculating? This ammeter, if I try to move it towards the battery, can I? If I try to move it towards the battery, nothing is blocking it. So this ammeter is actually calculating the total current. Okay, I repeat. When the ammeter, I try to move it towards the battery, nothing is blocking it. I don't have to go through other path or whatsoever. So this ammeter is measuring the total current. In order to calculate the total current, that would be because in order to calculate the current, all right, you don't have to go and measure the current passing through here, the current passing through here, the current passing through this part. No need. All you have to do is V total, remember V equals to IR, I total, R total. V total is 5 volts. This is V total. R total is the effective resistance. So the current that passing through the ammeter is the value of the battery divided by the effective resistance that we just calculated, 5 divided by 10, 0.5 ampere. So that's the current flowing through the ammeter. Okay, and finally, the last question asks us, calculate the potential difference across point AB. AB is here. All right. AB, we have resistor 3, resistor 4, and resistor 5 here. Okay. So, meaning means if I want to get the potential difference across AB, I look back over here. I want to find, this is AB, yeah. Let me use another color to let you guys show. This is point A. This is point B. Don't complicate yourself. This is point AB. This is the potential difference we want to find, VAB. And then I simplified this 3 resistor into 2. So this 2 point is potential difference AB. Okay? Then I simplified R resistor 3 and 4 and resistor 5 to a combination of R3, 4, 5. To like this. This is potential difference AB. Now, why did I do that? Because in parallel circuit, the current is summation. So if I want to find the potential difference across A and B, I need to find the current that passed through the top and the current that passed through the bottom, which is very tedious. Alright, so that's why when I go to this circuit, I combine resistor 3, 4, and 5 to become one equivalent circuit. This is connected to the ammeter, connected to the power supply. So the current that we calculated at B just now, which is 0.5 ampere, it will pass through here at 0.5 ampere. Across resistor R34, passing through R2, R1 is all 0.5 ampere, which means, okay, which means using here, I'm going to erase all this off. Which means I perbesarkan my diagram. This is resistor 3, 4, and 5. A is here, B is here. I want to find the potential difference across AB. The current that passes through this equivalent resistance is the current that passes through the ammeter, which is 0.5 ampere. So in order to find VAB, I need to multiply by the current that passed through the ammeter, multiply by the resistance of 3, 4, and 5. So VAB equals to 0.5 multiplied by 345 is 2 ohm just now. So 0.5 times 2, 1 volts. Okay, so that is 1 volts, right? That 1 volts. Are you okay with this explanation? Point out short scenario again. I hope you're okay with it. Boleh brain lah. Okay can understand hopefully Alright, so since I'm not going to be editing anything. Once the video is done processing by Google, I will actually directly upload it lah. Okay, I'm gonna stop recording first.